Monthly Space News. It's a rather shortened one this time. Normally we go a month between meetings, but we had to meet a week early this time, so it covers slightly less time. What we'll be covering a little bit on the Terran-1 launch. It was sort of a failure or a partial success, depending on how you spin it. We'll spin it both ways. It does have some implications for 3D printing in general and methalox as a fuel, meaning methane and liquid oxygen combination. And part of why they were a success or partial success was they got through the most stressful part of a launch. It's called the period of max Q. So I'll talk a little bit about that just because you tend to hear it, but I'm not sure if everybody knows where it really came from. Most of the time we'll actually spend on orbital debris. NASA just came out with a new study on what they think is going to be cost effective for getting rid of some of the orbital debris. That's what this picture on the left is representing here. Other miscellaneous news, and then talk about briefly about just some of the recent launches that we've had into space. So, the launch of the Terran-1, which was a rocket from relativity space, is a brand new one, hadn't been launched before, ever. It did fail. Actually, the first stage worked fine. It was the second stage that failed. So what are the key points about Terran-1? Well, one is this 85% 3D printed, which is unusual. Actually, Rocket Lab, they print their engines 3D printing, so it's not exactly unknown. Probably most people making rockets use them to some extent. They just are carrying it much, much further. They're building the whole structure, tanks and everything. The second part of the thing that makes them a little bit unique compared to the old days is that they use methane and liquid oxygen as their propellants. It turns out that actually almost everybody else is now too, but nobody has actually gotten to orbit with this yet, so there's kind of a race going on. One thing about this was back when these companies were founded, which wasn't all that long ago, everybody was enthusiastic about building small launch rockets, and everybody thought that'd be a great market. And there were lots of other companies like Rocket Lab and Astra and some of the others. They all thought it was going to be great. What they've realized is actually there's not much of a market for it. The real market is in launching constellations of bigger satellites. And so this one is probably doomed in the sense that it's an expendable rocket, kind of like the old school rockets. You don't use it once, you can't reuse it. And as a result, it just costs more. So it's probably doomed from an economic standpoint anyway. But the basic problem is that the payload is too small to get real market share. But they kept going with it as long as they did, partially because they had contracts to use it, but also partially because it's really a proof of concept for the rocket they really want to build now, called the Terran-R, which is more like a Falcon 9 competitor, kind of medium lift kind of a rocket. And so this is actually a good way for them to demonstrate that they can do 3D printing, they can make it work, and now they just need to scale it up some. And they're pretty far along on doing that. So as I said, the second stage failed, but the first was okay. So they did not make orbit. They will be focusing really on the larger rocket. The larger one, the Terran-R, will be actually a serious competitor for the SpaceX if it actually, when it actually works.
I might point out that that little white splash down at the base of the Terran-R picture is actually a human being.
Yeah, I should have said that, yeah. Which makes it kind of comparable to the other medium lift rockets. So anyway, this one will have a reusable first stage and a reusable second stage, and the fairing, which is the nose cone that opens up in most rockets. They actually are apparently going to keep it attached to the second stage. They'll just recover the whole thing all at once. Anyway, it will be a Falcon 9 competition, slightly less payload, but pretty much that's it. So it did partly succeed because it showed that the rocket is strong enough to get past the most stressful part of the launch, which is called the point of max Q. And actually you hear this sometimes in other launches as well. But what is that? What does that mean? Well, again, it's the point where there's the maximum mechanical stress. But why is that? Well, there's this thing called Q, which is dynamic pressure. That's the word for it. There's an equation there. It's just essentially it's kinetic energy. You're used to seeing 1/2 mv squared for kinetic energy. So you take that same mass and you just divide it by the volume, and we get the density, and that's what that is. That's just basically representing kinetic energy. And what is that? Well, you stick your hand out when you're driving in a car, you feel the pressure, and that's what dynamic pressure is. So if you're standing still, you won't feel anything. But if you stick your hand out of a moving car, you feel something. It's beyond the normal atmospheric pressure that you're experiencing. So, in fact, literally, Q is the pressure you would get if wind. Say you're standing still and wind is hitting you. The wind comes to a complete stop. All that energy essentially builds up, and it kind of builds up the pressure, at your outstanding hand if there's a wind coming. If you take the point of view of being on your moving car, you think you're standing still and the wind's coming at you. But either way, essentially, they're coming together, and all that energy is going into pressure. Now, that's not the real situation, but it's a good approximation for what's going on. The units are pressure, like pounds per square inch. So you have the notion of a total pressure, which is basically this dynamic pressure plus whatever the atmospheric pressure is. So we're sitting here in a soup of 14.7 pounds per square inch of normal ambient pressure. If I run really fast, there's a little bit of extra pressure against me. So another way of looking at it, though, is that what is Q? It's the difference between the normal pressure and the pressure you're experiencing, say, at the front of a rocket or something. And that results in stress because you apply that pressure over an area, you get a force. And as a result, there's forces. And the maximum Q is where you're going to get the most stress mechanically. So some examples. At the start of a launch, or for that matter, if you're just in a car standing there, not moving, the Q is 0, no dynamic pressure. And you can see that right from the equation, in fact, there. If rho is atmospheric normal, but v squared is velocity squared. There's no velocity, the value is 0. At the end of a launch, typically you're up in space. Well, there also, you basically have a value of 0 because the density is essentially 0. There is no air up there to speak of, a few molecules here and there, but basically it's close to 0. So you start off with launch at 0, you end up at 0. In between, you've got positive value for density and you've got some velocity. So there's some values in between. There has to be a maximum somewhere. That maximum, that's where max Q is. So during the launch, as you go up, your velocity starts off very, very slowly. It kind of builds up as the speed goes up. But at some point, what ends up dominating is the fact that there's no air left. Density goes down to 0. So that kind of gives you some examples of extreme cases anyway. Remember the movie The Martian, where there was all this damage done by wind and everything? That was actually just totally ludicrous because if you're getting blown by wind, say 100-mile-an-hour wind on Mars, well, the density is only 1% of the density on Earth. And just from that equation, which is an approximation, but it's, from that equation, basically that's equivalent of a 1-mile-an-hour wind. So that 1 mile an hour was not going to blow you over. It wasn't going to blow over your car. It wasn't going to knock over the greenhouse. None of that kind of stuff. So, but yeah, I know Hollywood can't get everything right. But that's just another example that, this is a real thing. We don't really have to worry about getting blown over when we're walking around on Mars. Just not going to happen. You might object a little bit and say, well, if we said that the Q is if the air goes all the way up to your car or a rocket or whatever it is and stops completely, you say, well, it doesn't really all stop there. Most of it kind of slides around it. That's true. But there are other forces that come in as well, lift and drag. So if you've got the rocket going up, there's friction essentially against the air. Well, it turns out that that force goes up exactly the same way as the dynamic pressure. The equation's there. I mean, people that have raced cars worry about the coefficient of drag on their car. As the speed goes up, the square of the speed, that's how much air resistance you're getting. It still comes down to that value of Q being a part of the equation. So if Q is at a maximum value, multiplying it by a drag coefficient in an area doesn't change where the maximum occurs. So fundamentally, this is actually a pretty useful concept. So anyway, they did that. They showed that they can get past that point. So they take that as a good thing, that it's all smooth sailing from here. By the way, I should mention, this is actually a serious thing. For instance, the space shuttle, when they're getting up to the point of max Q, they actually throttle back on their main liquid engine. You can't do anything about the solid engines. You just light them and they just go. But the liquid engines, they cut them back quite a bit. And as a result, they weren't going so fast while they passed through it, and they got past it. Then they go back to full throttle again.
Throttle up.
Yeah, exactly. You'd hear that kind of thing, go for throttle up after it. So it all comes back to this whole dynamic pressure idea. And people really worried about it because they don't want the rockets to get torn apart by the stresses. Okay, and then the other part of this is the methalox notion. Methalox is a portmanteau word. Methane plus liquid oxygen, which is abbreviated LOX, L-O-X. And actually, LNG kind of counts in there, liquefied natural gas, because that is really mostly methane. I mean, there's very loose specs on that. It might be 85 to 95% methane, probably close to 95% most of the time. It really gets lumped in there. The next component in that LNG is going to be ethane, and actually its properties are pretty similar to methane anyway. It's just a little bit heavier, a little higher heating value. It's not that different, so you can pretty much treat it. So when people talk about this race to orbit for all the people that want to build methalox rockets, they include LNG. In fact, if they are going with pure methane, they probably are getting it out of LNG in the first place just by further refining it. Anyway, no one has got to...
If you had a methalox rocket, you could go down to the corner convenience store and get a bunch of those LNG canisters and use them for fuel.
It's very inefficient, but and probably very expensive, but you could do that. Yes, you could. Okay, so I'm saying here it's kind of a race. Well, really, you go, how come I haven't heard of this? Well, actually, almost everything coming along is methalox these days. The relativity space ones, the Terran-1 we just talked about, and the newer one, Terran-R, they're there. And I'm going, as I come down this list, I'm going left to right on the rockets here, so you want to get a feel for their roughly their heights. This isn't exact, but it's pretty close. So there's that. There's the neutron, which is coming from Rocket Lab. They too realize they can't make money just selling small rockets. So really, they're making most of their money from selling satellite parts right now, and satellite buses and stuff. But they do have a new rocket called the Neutron coming in, which is more, again, basically all these are Falcon 9 competitors. United Launch Alliance, their new rocket, the Vulcan, that one, it happens to have a Blue Origin engine, which is also a methalox engine. So it also is going that way. And then, of course, the Starship from SpaceX. And then there's one that most people probably haven't heard of, is a Chinese one, often just called ZQ-2. It's already been tested, exactly the same as Terran-1, back in December. I think I reported on it at the time. It was the first, but it was just like the Terran. The first stage worked just fine, but the second stage, they actually had an unrelated mechanical failure, and it just didn't work. They actually could be the winner. They're almost ready to launch their second one. So they actually could come in first. It's pretty close. I mean, there's a whole lot of these rockets. They're all happening this year. So it's really more an issue of bragging rights than anything else, but it is pretty close. So why is everybody going to methalox? And not everybody, but I mean, why is it becoming such a standard? Well, first of all, it's just a heck of a lot cheaper. Because you can derive it from, say, from fracking as a result of the U.S. sources, or LNG if it's shipped over there, it still is a whole lot cheaper compared to the other choices. Hydrogen, I mean, that's just really expensive to generate, in particular to store it and to handle it. It's that part that makes it so expensive. And actually, the same is kind of true for RP1. RP1 is just kerosene, but it's very highly refined. They knock out all the sulfur and a lot of other impurities that get in there. By the time they finish with that, it's this kind of thing they make in very, very small batches for a very small market. It's just really expensive. So it turns out methane, it's so much cheaper that there's really a compelling reason to use it. It matters now. In the old days, especially when you didn't have reusable rockets and you didn't have so many of them, so you weren't getting the efficiencies of mass production, nobody cared about the cost. Now, actually, the propellant is becoming a higher percentage of the cost of doing a launch, and now it starts to matter a lot more. So that's one of the reasons we're moving to it, compared to either hydrogen or kerosene, which are the two leading liquid fuel contenders besides methane. Now, there are some specific benefits compared to RP1, which is, as I said, our highly refined version of kerosene. That's what the Falcon 9 has. Now, and they're obviously making it work. Can't sneeze at it. But methane is a whole lot cleaner. That means, in particular, even before you burn it, you know, in the fuel lines and everything that go to the engine, it just doesn't leave residue of any sort. So that stays clean. And after burning is even more noticeable. You get a lot of coking, soot generation, that kind of thing. Basically, a lot of partially burned substances, mostly carbon. You get that buildup, and then what that says is you got to clean it out. And it just takes time. And so the less of that you have, the faster you can turn around your rockets. One of the big things about reusability is fast reusability. You want to get the thing back in circulation. You know, if you're flying a plane to Tokyo, it's great that we're reusing the plane instead of throwing it out. But you also don't want it to take 6 months to get ready. The faster you can turn it around, the more efficient it is. So methane is cleaner. You can see that down there at Space Center Houston, actually. They have a Falcon 9 down there. And if you take a look at that thing, it looks pretty grimy. And you think about it, well, that's a booster. It's landing in its own exhaust. And it's just kind of dirty. Yeah. So kerosene is not a clean burning fuel of any sort. Now, also, the other comparison is methane compared to hydrogen. And hydrogen is still used quite a bit, especially in upper stages. It's very efficient as a fuel. And SLS, for instance, is one that uses that. But the thing is, you got to store it. You got a rocket. It's got to have big tanks of fuel. You can store a whole lot more energy, in effect, with methane, or RP1 for that matter. Hydrogen is kind of bad in that regard. The other big thing is, of course, hydrogen is extremely cold. It has to be very, very stored, very, very cold, much more so than either the liquid oxygen or the liquid methane. So you don't need as much weight for the insulation. There's a lot less thermal stress to have to worry about. You have to make sure that metals don't change temperatures too fast when you're loading it up. I mean, all those things just add all kinds of problems. In fact, you can even have a common bulkhead, meaning in between the liquid oxygen and the methane, you can just use one piece of steel. You know, you don't even have to have separate tanks because they're essentially almost at the same temperature. Hydrogen has other problems like it embrittles metals, which matters a lot. It doesn't matter if you're using it once, but if you want to use it dozens of times, you start to worry about the hydrogen embrittlement, meaning it gets brittle and actually can break. Leakage is always a problem with hydrogen because it's just simple, smaller molecules, and they leak. It's always a problem. But in terms of efficiency, it's actually pretty close to hydrogen. It isn't quite as good, but it's getting close. And then there's the other thing that's kind of in the back of people's minds, especially Elon Musk. He wanted to be sure that he could build rockets that ran on fuel that could be refueled in other planets like Mars. It's not that, in principle, it's not that hard to generate methane as well as the oxygen on Mars. You have carbon dioxide in the atmosphere, and you have oxygen in the water, that all that's there. And so with fairly simple, relatively simple chemistry anyway, you can do it. Now, it's still obviously going to be a big engineering challenge to do it at scale, but it's clearly doable. It seems like we better get used to doing things with methane. And that's kind of the view that people have taken, even though it's admittedly more something in the future.
Yeah, because MOXIE was successful on Mars, right? The little MOXIE,
they were just using it to generate oxygen. That's one of the key reactions, is splitting the carbon. You take the carbon dioxide in the atmosphere is mostly carbon dioxide. You split it in. The main thing was just a proof of concept. But yeah, so they know they can do that part. They wouldn't do it exactly the same way, but at least in general, on a pilot scale, that works. Okay, so moving on to the next topic, NASA did a big study, cost-benefit analysis for different ways of removing orbital debris. And you've seen these kind of graphs before showing total number of objects in space is going up and up and up. In fact, even the ones that are actual spacecraft, the blue line on this graph, you see they're really shooting up. And it's just because there's all these constellations of satellites going up, Starlink, OneWeb. The Chinese are going to put up 3,000 satellites pretty soon. Everybody's just throwing lots and lots of satellites up there. The number of rocket bodies isn't going up as fast. What happens typically, the first stages always fall back to Earth, either uncontrolled or controlled, but one way or another they go back. But the second stages and higher typically get stuck up there. And so they just are tumbling around. But we're packing more and more satellites into each rocket, so the number of objects is going up faster. But then the big problem is the debris. That's the dashed purple line here. And there were some big jumps, like, for instance, there was a Russian anti-satellite test that did one of these jumps. There was another one, was a Chinese one, and there was one where there was just a collision between a Russian satellite and an Iridium communication satellite. So every time you get a collision, you get extra debris up there, and it's just building up and building up. So, that's been a concern, and so people are wondering, what can we do about it? Well, they studied this, and they looked at the problems. They tried to put it in terms of actual cost instead of just doing it as a moral issue. So they said, if you have debris up there, you have to maneuver around it. That costs you propellant. That also costs you analyst time, even to figure out what to do. People have to make decisions on this kind of stuff. But then, of course, you're actually talking about the safety of astronauts, but also the safety for the other craft that are up there. As I said, there was a crash between an Iridium satellite and some other stuff. It does happen, and then there's an economic loss there. Now that, of course, you have to weight by probability. So the whole thing is based on expected value. You say, okay, it might cost you, $10 million, but it's maybe a low probability. We just multiply the probability to come up with someone, get an idea for, what the cost might be. So what are the methods for reducing debris?
One other thing is that this is a real problem because they didn't think there was a very high probability of this debris being significant. And then twice in the last 4 months, the Russian spaceships have gotten holes in them, spitting out fuel or some kind of liquid into space. Yeah. Now,
of course, they're saying it was just a micrometeorite. I mean, there are always things up there doing it. Of course, they're not going to ever admit that it was one of their own anti-satellite tests that did it. And we will probably never know. Well, they were trying to blame American astronauts for using ice picks or something, too. I mean, there was just, all kinds of crazy stuff there. Blame everybody but yourself. That's the general rule. Okay, so anyway, reducing the risk associated with debris, there's really 3 ways to attack it. The first one is simply don't create it in the first place. So for instance, there are protocols. The standard really is to make sure that if you have a first stage that goes really high or even a second stage, make sure you can actually deorbit it. Or if you have a satellite up there, make sure you have a plan for deorbiting it at the end. And there's various ways of doing that. We talked about some last time. Dropping a tether, which increases air resistance and in particular interacts with the Earth's magnetic field, slows the thing down. There's lots and lots of ways to do that, and it's being done, actually. So that's one way, and that's been attacked at least. The second thing is simply to improve the tracking and characterization. And then at least you can do more collision avoidance, because sometimes people just get blindsided. They don't even know it's coming, and then it hits them. And maybe the space station is an example of that. But then the third approach would be to remediate the debris, basically try to go around and collect it one way or another. You need a garbage truck up there to pick this stuff up. And so that's really what the focus of this study was. It was remediation, not avoiding it, but remediation. They just said, okay, let's just do a couple of scenarios. Look at large debris, meaning more than 10 centimeters. People before have identified what are the 50 that are the most concerning pieces of junk that are up there that people are worried about. And say, okay, we'll just do a case with that and see what it takes to remove those. And then for small debris, that is between the 1 to 10 centimeter size, They said, okay, what if we removed 100,000 pieces of that? Because a lot of these objects that I was talking about in that graph up there, I don't think they go down, they don't even go down to 1 centimeter. There's a lot of really small stuff up there. By the way, these scenarios did not include the worst cases, the Kessler cascade kind of thing, where something happens and it makes some debris, and then that debris hits more things, and the whole thing kind of builds up. They didn't actually think that was that likely yet. They factored in one additional level. If 2 pieces of debris collided, that it would generate some more, but the probabilities dropped off. They didn't see that coming right away. But what are the benefits for it? We talked about the satellite operators. They actually have to use their propellant in their satellites to move around, if they can. Not all satellites can maneuver, but most of them have some maneuvering capability. Surprisingly, that really is very few dollars per year, $58 million a year, which is really not that much. A lot of people were surprised at that, including the guy who runs OneWeb, which is the next biggest competitor right now to Starlink. They have maybe 600 satellites up there, and they're just starting their internet service now. He says they actually get 53,000 warnings a day from the Space Force. Now, those things must be covering some pretty big distances, but they act on 6 to 8. They actually take maneuvers 6 to 8 times a day, they're saying. Now, that sounds 600 satellites or whatever it is. So still, that gives you an idea, though, they're doing a lot of this. What is the cost of that maneuvering? And one thing that I thought was kind of odd about this study was they decided that, well, while you're maneuvering, you probably are not able to use your satellites for the intended purpose. Like you're probably going to interfere with communications and so on. So they said, okay, there's a cost for that. You're going to lose some revenue if it's a commercial satellite, or if it's a military satellite, you're losing the ability to monitor some war somewhere. So they counted that, but they didn't count for the fact that if you use up your propellant faster, ultimately the satellite can't stay up there as long as you've got to deorbit it because it's about to run out of fuel. And normally you save some fuel at the end for deorbiting. They didn't count for that. And that strikes me as a much bigger dollar cost. You might lose a year. If you lost a year out of a 15-year life at satellite, that's pretty significant. So anyway, it didn't look to me like they actually accounted for that, but they tried. They made an attempt to cover a lot of things. I think they just might have missed a few. Yeah.
We have a question from the online cohort.
Yeah.
Please explain why OneWeb will get Space Force warnings.
General service. It's true the United States probably does kind of assume a lot of responsibility because there aren't many countries that can actually track all this debris. And we probably are the most transparent about it, but somebody has to, so we've been doing it. We do it because we want to defend our own satellites. We have the most at stake by far, so I think it's probably our own self-interest. We have the most to lose from collisions, so we probably better do our best to prevent them. That's my guess. Okay, so they studied a whole bunch of methods, and I'll actually give some examples of what these look like, but they said there's several approaches that might work the best. For small debris, they actually want to, what they quote, nudge, basically the small pieces of small debris with lasers, either based in space or on the ground, and we'll talk about that in a minute, because it's probably not what you're thinking. But they claim that would be a 10 years investment. You'd get back your money in 10 years on that one. To me, it seems to me that there's probably a lot of R&D involved in this, because you're talking about hitting pretty small pieces of stuff pretty high up. They're moving pretty fast. It's pretty high up. Now, the thing is, this goes back to the 1980s military, Strategic Defense Initiative, or Star Wars, as they called it back then. They did a lot of research on using lasers and other things, for clearing out stuff in space back then. And a lot of this research really goes back to that period of time. You wonder how much of that is classified and can be used or not used. It wasn't clear, and they really glossed over that in this report, I thought. The other thing about using lasers, though, is that would trigger concern from everybody about their use as weapons. Anything that can take out a piece of debris can take out a satellite. It becomes a weapon of war. The claim was that the lasers they're talking about would not really be powerful enough to really do any serious damage to a normal operating satellite. Seems a little questionable, but anyway, that's the claim. And they had some study to kind of back that up. That's handling small debris. For the large debris, they said the best thing right now is pretty much just doing collision avoidance. And you do that by nudging the debris, again, with lasers or using small rockets, one way or the other. So you don't necessarily get rid of it and deorbit it, but at least you knock it out of the way, one way or the other. And they're saying 10 to 20 year break even for that. So what does this stuff look like? Ground-based laser. I mean, this does seem like Star Wars all over again, but you got some piece of debris going over here, and it's going from right to left across this screen. The initial orbit. And what you do is you zap it. But the thing is, you're not just vaporizing it, which is what you're probably thinking, because that's what it looks like. Actually, it's more obvious in a space-based laser case. Essentially, you're doing the same thing. You're just doing it from a satellite. If the debris is heading from right to left in this picture, if you zap with a laser in a very, very tiny little area, it'll ablate it, meaning it'll blow off pieces of it, and it's all going to be directed in the opposite direction of the orbit. That generates enough momentum that it slows the thing down, and eventually, as you see back in the previous one, they show that it'll take it to a lower orbit. You get it down low enough, and air friction will take care of it. You don't really have to get it all the way to the ground. You just have to get it low enough for air friction to become significant.
I imagine a lot of this material is like spinning. How does that affect?
Well, that's actually one reason in particular that they favor the laser approach, because what they do is they use a pulse laser where it's extremely intense for a very short period of time, and so it isn't going to spin that much during the period it's hitting it. In the mechanical means, if you're talking about collecting a big garbage can one way or another, it's kind of hard to grapple it when it's spinning very fast. So that's actually one of the reasons why they like the laser. The key thing is that you deliver a lot of energy in a very, very short time.
Yes, the DOE does have nanosecond and picosecond lasers
Yeah.
already.
Some other approaches that you might think of, they say would really cost a lot more. Space tugs are the obvious one. You go out and you capture the stuff one way or another. The difficulties are, as you brought up, spinning. If they're spinning, it's just very hard to grab a hold of something. That's a lot of angular momentum. You're going to pick that up. So if you're up there, all of a sudden you're going to start spinning with it too. It's just hard to deal with. And it actually ends up just being a pretty expensive way to go anyway. But there is something related called a sweeper spacecraft, where pretty much just put up a big panel of very thick, strong cloth like Kevlar or something. It's shown in this thing here, where basically you just stake out an area and you just go through it with this big hunk of cloth. And you don't actually try to catch it, you just try to slow it down. It'll probably just penetrate, go all the way through it, but it'll slow it down enough. And again, eventually it'll get low enough, the air friction will take over and it'll go out of the atmosphere. And they said that should work, but it'll take 20 to 25 years to get back a return on that. Part of the problem is space is big. You can make this thing pretty big, but you're not going to hit very many of them. If you're just kind of up there just doing a general sweep, it's pretty hard. So unless you have a very specific area where you know there's a lot of debris, it's going to take a long time. With the lasers, they're basically just saying, watch, just wait and watch. You pretty much scan one area of sky. When you see something, you immediately zap it. And that's what I was saying. That also will take a lot of time, but at least it's you probably can cover more ground that way, or more space that way.
So this is basically like a big Swiffer in orbit.
Yeah, pretty much.
Or a catcher's mitt.
Well, it's a bad catcher's mitt because it lets the baseball right through, but at least it slows it down enough. Yeah, yeah. Now the other one is a little more exotic, or a lot more exotic. That they say actually is sort of promising, but it's going to take a lot more R&D, and that's recycle the metals. They've been funding through SBIR's Innovative Research Small Grants, orbiting foundries, where the idea is you repurpose the metal. This is more of a grappling kind of thing, but once you do that, you just melt it all down, very, very hot. And what's interesting is that they say they can actually make propellant out of that. There's a type of rocket engine called metallic plasma propulsion, where essentially you heat up just the tip of the metal and it goes shooting out, and actually aluminum works just fine as a propellant. Or alloys. Typically what's up there is going to have a lot of aluminum and have some other stuff. You're actually able to use that as a propellant. Anything that you can shoot out, you get a reaction from it.
Molecular, right? It's not really particles.
No, they're actually talking about doing a wire. They'll have a wire and they just burn the ends of it.
Right. When they burn the ends of it, what's emitting is not a particle. It's almost a molecule.
Yeah. Well, actually, it's actually plasma. So that's actually not really a particle. It's another state. I'm
just thinking about you might be creating exhaust from that engine might be a problem after a while.
Well, apparently they don't think so. Apparently, whatever coalesces after that, from when plasma coalesces back to something else, it must be such fine particles that nobody ever notices it again. That's the principle. So in a theory, you could have kind of a circular economy in space where you got all this junk up there, you go and you find one. And by the way, there's all these companies that are working on kind of a project on this thing. Astroscale has been working on capturing small satellites. NanoRacks has worked on cutting them up, using robotic arms and lasers to cut them up or weld things together if they need to, but basically cut them in small chunks. Cislunar Industries has a technology for basically melting it and generating the wires. So they're all kind of working together on this as a project. Okay, now the trouble with recycling is the same problem we talked about with asteroid mining, that actually we're getting better and better at lowering the cost of getting up to space. So if you want to manufacture stuff in space, like wire rods, well, you're competing against ground-based wire rod production, and the cost keeps coming down. This is a slide just showing how costs have been coming down. We've had various slides like this before. I just hadn't seen this particular one before, where actually the shuttle was like $60,000 a kilogram to get stuff up there. And they got better over time, but still, it took, until you got down to the Falcon 9 here, that was already a factor of 10 cheaper. And actually, Falcon Heavy is even cheaper than that. And the next one didn't quite show up here, but the next one, when you get Starship, it could be another factor of 10 or more. It's going to get that much cheaper. So actually, if you're going to try to make money by reselling stuff in space, in a way, it's almost unfortunate that we're going to have such cheap access. I'll take that trade. That seems worth it.
This is something about scale.
It's a log scale. So yeah, this is not linear. So we're talking, $60,000 up at the top. We're talking down here in the below $1,000. So yeah. Okay, so this is their summary slide, pretty much showing the benefit analysis. And what they do is they're plotting plot it as a year. How many years would it take to get your investment back? When you've assigned a monetary value to all this stuff. And so they show that for the small debris, which is the left-hand side of this picture, the ground or space-based laser were cheapest. The sweeper was a whole lot more expensive. For the large objects, they split it out into controlled and uncontrolled reentry. Controlled reentry means you actually direct it to a specific spot, usually the Pacific Ocean somewhere. Under uncontrolled reentry just means you get it low enough and eventually it slows down and falls down somewhere. If it's a small object, at least it'll vaporize before it hits anybody. Now they're saying the laser or the rocket, JCA is just-in-time collision avoidance. That means you just basically do a lot of diversions. They're showing a wide range here. The problem is they seem to be assuming the technology exists already, and I'm not quite sure that's true. But it varies a lot. I mean, if you have an opportunity, you would take it. It's hard to say. I don't know how they came up with the variation here, but these bars indicate a variation in a number of years it takes to get your money back. And the recycling option, they just said, well, there's a lot of R&D involved in this, so it's going to take a lot of years to get your money back. And that's the best they could do. Okay, now, of course, there's a huge debris problem coming up, actually, in a few more years, 2031. The end of life for the space station is going to be 2030. And what NASA is saying is they want to come up with some kind of solution for getting rid of this. And they say they probably would deorbit it in 2031. Maybe you launch craft up there to help propel it. They have a whole separate request that's gone out for proposals from industry on what do they do with this at the end of its life. It's a huge debris issue. And actually, all the techniques we talked about, some of them may well apply here as well as just having a giant garage sale, selling off the solar arrays and everything else. I'll talk about that next time, just to keep time down. I decided not to cover that this time, but this is the big one. It is coming up here. Other minor news, Virgin Orbit. Now, they're the company that does launches of small satellites to orbit by dropping them out of a plane. The idea is you get it up, going as fast as you can, as high as you can, you drop it, and so you save some of the energy. This is not the same as Virgin Galactic. It's a spin-off, actually. That's the one you normally think of, where they have a different shaped plane where they take people up. This is strictly for small satellites. And they're having real trouble. They laid off 85% of their workforce. They're essentially stopping operations. So they probably have a very short life ahead of them. They were trying to get funding, and they didn't get it.
This was probably related to their failure last month.
Well, I'm sure that didn't, yeah. If they had succeeded, this was the launch from England. If they had succeeded with that, then that probably would have gotten people a lot more enthusiastic. But the fact that they failed made it worse.
It was basically like a small launcher.
Yeah.
And so you're running it again into that problem.
Yeah.
The small launcher market.
Yeah. Well, there is a small launch market, which actually, well, what it is actually, it's turned out it's mostly military. The military wants to be able to respond quickly. If somebody blinds one of your satellites or something, they want to be able, within a couple of days, be able to get something up in its place. But that's their ultimate goal, is to be able to do that. So with small satellites, typically, it may be an offensive capability too, but at least they want to have that capability. And so they're pretty much keeping that whole sector alive. Either that or people like Rocket Lab are simply branching off into other things. Okay, so how many launches have we had since the last meeting? Now keep in mind, it's only been 3 weeks. So you might think there might be a smaller number of rockets than normal. Well, okay, I might as well wait for
100.
You're coming down again. You're all getting really, really close. Yeah, Doug is famous. He started off with 10 million or something. He comes down by a factor of 10 each time. Sooner or later, he's going to get it. It turns out the answer is 19, which actually is pretty good for, maybe 21, 22 days. It says we were almost launching once a day. And they're actually kind of typical. It's just a smattering of things. I mean, the Russians launched military satellites. SpaceX launches commercial satellites, and the Chinese launch something in between. You can't quite tell with them. I think we've actually covered a lot of these. The big one, the Terran, of course, was kind of a notable one. I don't think it's worth really talking about too much. Any of these others? Second page here. Israel, every couple of years, Israel has to replace one of their military satellites, so they launch one. They have a special problem that they have to do a very energy inefficient launch because they shoot their rocket up. The problem is the only place they can drop it in the sea is off to their west, the Mediterranean. They don't want to drop it over a populated area. Only China does that to their own people, but nobody else wants to do that. So, but as a result, because they're losing the advantage of the spin of the Earth itself, which is a couple thousand miles per hour at the equator, they have to launch the other direction. It's harder for them to launch. But every couple of years, they put a satellite up. And so that it was their time to do that. Yeah, I think that's about it. All right. Any other discussion or questions?
So, any news when SpaceX is going to
I
finally commit to jump roll?
Yeah. Well, I think they're still waiting on the approval from the launch approval, probably.
That's holding up the show.
I think so.
They're starting to get clogged parking lot. They've got rocket boosters and spacecraft. They're building up. They're running out of places to put them because they're continuing to manufacture more and more of them, but they're not launching.